Of the, for example, like Ethereum, and current plan is to use the data availability technologies so that each node does not need to download all the data, but rather than just have the pieces of data and then be able to sample the data, the rest of data in the network to know that, oh, this data is guaranteed to be downloaded by everybody in the network. So that's basically the target of DA. And also that requires some like requirement in terms of CPU. For example, it requires some decent core number of cores of CPU with some memory and also storage. For example, a fresh Ethereum node now requires about 1 terabyte of the storage, and sometimes grows higher because it has to have some intermediate stage during the execution. So to solve the CPU requirements and also the storage, the basic idea here is to using some proving mechanism. For example, Ethereum proposal is for stateless NIST client, so that we can quickly verify the execution, because here we just need to validate. So we can quickly verify this execution of these results using low performance CPU, or the CPU can be smart contract on top of Ethereum. That is for layer 2. And very small amount of the storage just maintain some key minimum data using the constraint, resource constraint environment, which definitely can be our nodes, like in our cell phone or in our like iWatch, or the layer 1 blockchain, and that is the smart contract. So in the zk EVM category, it sometimes is called type 0 EVM. Why is called type 0? Because it's super general, and which means that we are able to using any language of code to write all this just like a normal execution client, and then we can proofread result, introducing, for example, new circuits in maybe different zk setup like Plonkish. So what is zkVM? Is generally we try to solve the problem or satisfactory problem that given a program and an instruction set architecture. For example, it can be MIPS, it can be Wasm, it can be x86. We want to verify that given the input-output of this virtual machine, and its execution result is correct. And so in order to verify this, we first need to choose ISA. So there are a couple of ISA that we can choose. For example, Wasm, RISC-V, MIPS, those are open source, which means that we can use them freely. And definitely there are also x86, which is proprietary, and ARM. And we have a compiler, which basically is able to compile any high-level languages to these low-level instructions. So on the right-hand side is assembly language called web assembly language. In terms of WAT format, tells what is a very simple instructions to add 2 variables. So here we choose to using the Wasm languages to prove a long execution of the Wasm. So that we can compile any high-level language code in the Wasm and prove the execution is correct. Why we want to using Wasm? Because Wasm is becoming most popular language in the internet. For example, almost all the computer with a browser supports execution of Wasm, and so that we also have a bunch of the tools that support execute the Wasm like languages or the compilation. And so next question is which language we would like to choose to program the blockchain, and then we would like to translate to a Wasm language that can prove by zk. And here we use the Golang. Why? Because Golang is perhaps one of the, I would say, easy to learn language with pretty capability to scale. So on the right-hand side is one of my favorite graph, which shows how many years, so 6 months to 1 year, 2 years, 3 years, 5 years. And then on the y-axis is the percentage of the programmer believe he's mastering these languages. So for Go, it just takes about a couple of months or 1 year, so that every developer is quite confident that they can understand how it works, can safely write the code. And there are a couple of other languages. I think there's one is C languages. Their curve can be even goes down, because when I use C language to write some code, I feel, oh, there's so many new features that I realize that, oh, I have to learn more, and then I realize, oh, actually there's a lot of things I need to understand. And so it's because it's so complicated. And I also have garbage collection, all these features that can also simplify the burden of developers. And in the Ethereum world, Golang is also widely to develop the client. For example, both famous like consensus client and execution client, the Golang implementation are the most popular ones. For example, Go Ethereum at the time of writing, that was about a couple months ago. Yeah, it's more than 80% of the adoption. Right now, it's a little bit decreased. And also, Prism is also written in Golang. And also, if we check the historical of the execution layer or consensus layer development, you can find there's a kind of massive effect that once the client has been adopted for more, then there will be more people to maintain it, to fix it, and then it become more stable, and then more people will come further to use it, and this goes to this circle that it will become more and more people using one specific type of client, and this is happening. And that's why even like Ethereum is encouraging for client diversity, but still a lot of people, including myself, is using Go Ethereum as my stakers. So now with all these environment setups, we would like to narrow down what we like to achieve. So that first of all, we want to compile the layer 2 execution layer that is written in Go. Sometimes we call layer 2 Geth or OP Geth, and then compile it into the Wasm. And then we have a Wasm verifier prover that can prove that this long execution of this Wasm code is correctly, so that we are able to use in very constrained environment, including, for example, layer 1 smart contract or even like iWatch, to verify that the execution is correct. And this is one of the, I think, the candidate for the future Ethereum endgame. And this is a really good starting point, but when we dive into the details to implement all this, they have found there's a lot of challenges. First of all, even though Wasm is widely adopted in, like, for example, for all the browsers, it is more suitable for an internet browser environment with very limited interfaces to perform, for example, system calls, like also, for example, create a connection, raw socket to connect to the underlying resources or accessing the files. So here we list all the basically key challenges, both in terms of the browser environment that Wasm, the compiled Go Ethereum in the Wasm that is basically looks like, so that we are not able to using the zk environment, because zk only have 2 inputs, private input, public input, done. So we need to change this kind of like host environment that is the interaction between the Wasm code and the host that's external environment. So to make sure that we are still able to execute the corresponding layer 2 Geth, but with minimum changes of this code. Second is that there's a huge diverge I/O models there versus Wasm, and also the Wasm model that's, as I mentioned, in the zk environment, that's public and private inputs. There's also a couple of others, for example, floating point instructions that is not able to support in most of the zk VM setup. And lastly is some like detailed implementation of Golang that have really weird execution, the exit semantics, which is quite different with what we expect. So, for example, here is a code that we compile the the Go Ethereum, the layer 2 Go Ethereum. And then we here list all the APIs that the Wasm code relies to. You can imagine kind of a system call so that they can execute the code correctly. And all these APIs, for example, have file descriptor read, file descriptor write, clock read, and all kinds of things are essentially impossible to be supported in a zk environment. How we are able to translate all those things into a zk-friendly interfaces with public input and private inputs. This is something we have to address. And so this is basically the target of zkGo. First, we do not want to re-implement the Go compiler into Go to the Wasm by ourselves. So we made a deep modification of the Go compiler, and so that with some modification, we would like to have it to be able to directly compile any Golang into zk-friendly Wasm. So the zkGo is basically open source, and we also work closely with our collaborators to make it happen. And I would say, our attractive feature of the zkGo is that it support most of the Go features. For example, garbage collection and Go routine is also supported, but written in the Wasm languages with this I/O, so that you just need about 3 dependency of the external host environment, public input, private inputs, and whether there's something that's wrong, then it will exit the execution of the Wasm VM early. And so besides replacing all this, we also have, for example, replace the unsupported instructions, like floating point instructions, called using a soft float, that is using the integers to mimic the execution of the floating point, so that we can translate single floating point instructions to multiple integer operations. And yeah, a couple of things. So let me see. Yeah, there's for floating point instructions. And so yeah, this is something I would like to show. So for example, suppose I would like to write a simple Go code to verify like a calculation of Fibonacci sequence. So if I'm using the traditional Go code, I will first read the data from, for example, from the CLI, and then do some calculation that is 1,000, and then finally I print the corresponding outputs. Because in the zk environment, we only have public input and private input, so that we will first read 2 public inputs from external, so that we are able to verify what is the inputs that the user supply during the verification. Do the calculation, and lastly, and then we verify that the corresponding calculation result equals the same as another public input. This is basically how the zk verification does. Like basically, I provide 3 public inputs, the first 2 variables and the results, and then the zk verifier will tell me whether it is correct or not. So it is solving this satisfaction problem. And since we are a Go compiler, so this is the so for using Go, we just go build the Fibonacci Go program, and using zkGo, then it has the same semantics to using. It just say, hey, I want to build the Go code, but the output will be the Wasm, so that it will be generate a Wasm code that can be directly proved by the zkWasm prover. For example, here we're using Definer's CLI, which provides kind of like some parameters, especially in terms of public inputs. For example, the first 2 initial variable of the Fibonacci sequence will be 0 and 1. And also would like to verify that the ending result is some large number after doing the Fibonacci sequence in like a 1,000 calculation. And then we can basically, using this CLI, we can prove this language and also create corresponding the verifier in Solidity, and then deploy this verifier and to make sure that the code is correct. So in this way, we greatly saves the developer, especially developers that would like to use in zk to solve their calculations without writing any circuits. Just write a Golang code, whatever you want. It can be even complicated as Go is there. So for example, one application that we are going to solve is to verify the off-chain execution of the layer 2 Geth, layer 2 execution layer, so that we are able to, for example, to use in a zk for proof, tell that the layer 2 sequencer, when it posts some result, I can instantly challenge that something is wrong. So the previous design using a binary section, which I actually explained yesterday, that it takes about 73 interactions of on-chain in order to figure out which instructions is incorrect, and also need to take about 7 days to settle. So using zk, now we are able to program all this layer 2 in Geth, compare it into Wasm, and prove it using single transaction and verify on-chain if something is wrong. So this is the basic idea of zk fraud proof. We are glad that we received a grant from OpenStack to support us to do the research in this area, together with Zhou and also O1 Labs, which are talking for different ISA. So Zhou is talking for RISC-V, and O1 Labs is talking for MIPS. We are targeting for Wasm. And so the general goal is that we are able to have much shorter latency, just proof time plus one-time transaction, and tells that, hey, there's something wrong on the off-chain execution, and for any general purpose like a layer 2 Geth. And one feature I like most for the zk fraud proof is that it can be easily to upgrade to support new Ethereum EIPs, for example, 7702, because it compiles any, for example, layer 1 changes, new changes to the layer 2, and compile into Wasm, and directly prove using zkVM technologies, so that the cost of supporting the upgrade is almost negligible, versus in the traditional zkVM, like type 1, type 2, type 3, if they would like to support these new features, in general, they have to re-implement the circuits and audits and all these highly complicated things. And it's called zkEVM scary. They are scared once there's an upgrade, introduce some, for example, new hash or new simple features, they have to re-implement all these things in the circuits, which is extremely difficult and very easy to produce new issues and takes time to verify. And using zkVM and proper approach, we can instantly support all the new upgrades. Just copy the layer 1 code to layer 2 Geth, recompile, generate the corresponding verifier, upgrade, done. So, and this will also help to contribute to the multi-proving system that we also participate with the Zhou and also the O1 Labs. And so we are able to compile the layer 2 execution engine, that is OP Geth, with some minimum modification of the Go Ethereum, but generally basically some I/O adaptation. And so now we are able to generate the whole Wasm, be able to compile, and then be able to prove it using the whole zkWasm setup. And so we can do a lot of things because we can basically prove any arbitrary execution. So one crazy idea is that we are able to prove a lot of off-chain database, like sampling, all these things using zkGo without writing a specific circuit. And also we are able to do a lot of off-chain calculation, for example, machine learning. And then we can using the basically zk for proof to prove that the off-chain interference of machine learning is running correctly. So we are also working with HyperOracle to help solve this problem. And there are a couple of interesting work to be done. One thing is to accelerate this proving procedure because this requires tens of billions of instructions, which is perhaps the largest proving system that we found in the world. And so it requires a lot of optimization, like using parallelization, multiple GPUs, so that they can run in parallel, and so that they can save the time, and also be able to aggregate the proof of the proofs. This is a general idea, so that we can aggregate them and then using a single proof to prove all these parallel proving results. We are also working on customized host circuits, especially for some instructions that are commonly used in Ethereum, like precompiles, ECC, Keka. We can use in customized circuit to support it so that we can reduce the trace of the we need to prove. And also a couple of new proving systems, like Vitali mentioned. There's a growing of the smaller fields, like Binance, all these smaller fields. And so how to be able to utilize these smaller fields and to incorporate to proving the Wasm code is a very frontier of this direction. That's all I have for this talk. So there's a lot of technical details, and I'm happy to answer more questions if you have. Thank you. Any questions? Sure.
Hello again. I wonder how does this compare with the existing zkVMs, like Starkware, for example, or even, I know this is not a zkEVM, so it doesn't necessarily run the Ethereum, the EVM protocol, but it does in any way, I guess, verify random or whatever programs. So it kind of relates with RISC-0 in a way, and also with Starkware or Cairo, even though those aren't necessarily compilable via high-level languages, but also like Polygon Miner and all these kind of high-level language compilers to Wasm. What's the main difference, or are just a competitor, not shaming it, just sometimes?
Yeah, that's a great question about the comparison with maybe other solutions like Starkware or, for example, RISC-0. I think I should really put a table for the comparison because I think I get too much details today. So compared to Starkware, first they have their zk languages ISA, so that they are able to prove the language using their Cairo prover, all these tools. One major difference is that for the Cairo, support of Cairo is still, the tool set is still pretty in the early stage. I know there's some idea that using Cairo write a lot of code to emulate EVM, like Kekara is doing. I think this is really interesting direction, but at the same time, one thing is that they have to re-implement all those things in the Cairo language. But for us, if people are familiar with OpenStack, so right now their layer 2, or layer 2 Geth is a minimum modification of Go Ethereum that is, I think, 1,000 lines of changes mainly to support the bridge between layer 1 and layer 2. The great benefit of this is that we are easily to reuse existing mature code of Go Ethereum that has been developed, which I show why it's being widely adopted, because you see a lot of people are fixing it, optimizing it. So yeah, so we are able to reuse all these benefits compared to Starkware. Need to rewrite this EVM stack in Cairo, and also make sure it is upgraded to the latest EIPs. If there's some Ethereum upgrade almost every year. So for those things, we do not need to worry about. We just, recompile, merge the code, recompile, and then submit a new verifier on chain, and done. So this is, I think, the great benefits versus the Starkware approach. Cool. Yeah, I think I'm run out of time, so happy to ask me a question. I'll be here. And yeah, thanks for attending my talk.